Hello everyone, my name is Ainemba Wasbrita and I'm going to talk about the two models that I trained according to our project. The first model is Transfer Learning Audio Classification Model, which uses a pre-trained network called YAMNet to extract acoustic features from chicken sounds. Then the second one is Transfer-Based Poetry Audio Model, which analyzes male spectrogram representations of audio using a vision transform. Both models start with raw chicken audio recordings, but they process the audio differently. I'm going to first talk about transfer learning audio classification model. With transfer learning audio classification model, the pre-processed audio is first passed into a pre-trained model called YAMNet, which acts as a feature extractor, and it analyzes the audio signals and converts it into 1024-dimension embedding vector. Then these embeddings capture important acoustic features, for example, frequency patterns, vocal intensity, and respiratory sounds, and then they are passed into neural network classifier, which learns to distinguish between house chicken sounds and house chicken sounds, and then the background noise. Finally, the model produces probabilities for each class using a softmax activation function, and the class with the highest probability becomes the final prediction. Then, with transformer-based poetry audio model, for it, instead of directly using the raw audio, the audio signals are first converted into male spectrograms, which represent the sound as a time frequency image. These spectrograms highlight acoustic patterns such as breathing irregularities and distress calls that may indicate respiratory diseases. Then these spectrogram images are resized into a 2024 by 2024 pixels and then fed into a vision transformer model. And then this model divides the spectrogram into smaller patches and processes them using self-attention mechanisms, which allows the model to capture complex relationships between the sound patterns across the time and frequency. And then these still extracted features are then used to make predictions about the health status of chicken sounds. So that was basically the explanation about the two architectures. I'm going to talk about how these models were learning. I'm going to start with transfer learning audio classification model. So with transfer learning audio classification model, we used a pre-trained model called YAMNet as a feature extractor, and these raw chicken audio recordings were first pre-processed and resampled to a sampling rate of 16 kilohertz to ensure consistency across all recordings. Then the processed audios were then passed into YAMNet, which converts the audio signals into 1024-dimensional embedding vectors, and these embedding vectors represent acoustic characteristics, that is the frequency patterns, vocal intensity, and breathing related sounds. After feature extractions, these embeddings are fed into neural network classifier, classifier that is composed of fully connected layers. During that training, we used a batch size of 32 samples, and the model was trained up to 50 epochs. Then the training process was optimized using the Adam optimizer, which automatically adjusts the learning rate to improve convergence and training efficiency. Then the training, after the whole process of training, the model achieved an overall classification accuracy of approximately 79% on the validation data. Then I'm now going to talk about transformer-based poetry audio model. For it, the raw audio recordings are first converted into male spectrograms, which transform the audio signals into time frequency representations that highlight important acoustic patterns such as breathing irregularities and distress sounds. These male spectrograms are then resized into 224 by 224 pixels, allowing them to be used as image like inputs for the deep learning model. Then these images are then fed into a pre-trained vision transformer model, which acts as a feature encoder, and then this transformer divides the spectrogram into small patches and processes them using self-attention mechanism to capture relationships between different sound patterns. During the training, the applied data augmentation techniques like adding small amounts of random noise and applying amplitude scaling were used to help generalize better to real-world farm environments, while the background noise is common. The data set was divided using 80% training and 20% training split to evaluate the model's performance on the unseen data. Then the model was trained using the Adam W optimizer, which improves the training stability and helps to reduce the overfitting through the weight decay regionalization. After the training of the 50 epochs, the transformer model achieved approximately 81% classification accuracy on the validation data, which is slightly higher than the transformer learning model. So that is how the two models learned, and also how they were optimized. So now I'm going to talk about the AI techniques used to audit the models. One of the techniques used is sharp analysis, which helps identify the acoustic features that contribute most strongly to predicting whether a chicken sound is healthy or unhealthy. And then another technique is live, that explains individual predictions by analyzing how small changes in input audio affect the output classification, and this also provides an insight into why a particular recording was classified as healthy or unhealthy. I also used other techniques such as saliency analysis and embedding visualization techniques, such as PCA, that is principal component analysis, which allows us to visualize how different sound categories cluster into the feature spaces. Yeah, so those are the AI techniques that we use it to audit the models. Then lastly, talk about the model evaluation. The performance of the models was evaluated using precision that measures how many of the sounds predicted as a certain class are actually correct, and also the recall that measures how many of the actual sounds belong to a class were correctly identified by the model. Then another one is F1 score, that provides a balanced measure by combining both precision and recall. Based on these evaluation matrix, the transformer-based model demonstrated a balanced performance in detecting both healthy and unhealthy chicken sounds, and this indicates that actually for this project, the best option would be transformer-based poultry audio model. Thank you for listening.